Sorry for the inconvenience, guys. Okay. What we learned in the last class? Okay, not see from first slide. Okay. In the last class, we will discuss about transmission line equations, right? Transmission line equations in terms of primary and secondary constants. So this is the transmission line theory and what is meant by transmission line. Okay, how do we define the transmission line, types of transmission line, okay, and the difference between low frequency and high frequency, and how that low frequencies are suitable for transmission lines and high frequencies are treated as a wireless transmission purpose, and how they are suitable. Metallic cable transmission lines, uh, okay, types of transmission line in that coaxial fixed pair open wire twin lead. Okay, already uh, we dealt with. And the metallic transmission lines in that balanced and unbalanced transmission line. Okay, what are the characteristics of the ideal transmission line? Yeah, what are the typical parameters which affect the characteristics of the transmission line? Okay, this is the equivalent circuit of the transmission line. Okay, remember that point. Okay, remember that diagram. Okay, it is very important. Okay, and what is meant by traveling wave? Okay, from the traveling wave, how do we define the traveling wave with some phase constant and a direction? Okay, see here, when the input voltage V of t, okay, the traveling wave can best describe it as Vc cos omega t minus beta z. Similarly, in the next slide, we will discuss about attenuation constant, right? Okay, already, and we'll learn what is meant by phase velocity and what is meant by group velocity. How do we define phase velocity? Phase velocity, velocity equal distance by time. From that, distance is the lambda and time is the inverse of frequency. From that, we define phase velocity is simply defined as omega by beta. Okay. Similarly, attenuation constant. What is the expression for attenuation constant? Okay, is it exponentially increasing function or decaying function? Okay, attenuation is always represented in the traveling wave of a transmission line is represented as exponential decay function as Vc, the e power minus alpha z, and cos of omega t minus beta z is the regular expression. E power minus alpha z is the exponential decay function where alpha is the attenuation constant. Okay, the attenuation constant is always measured in what are the units? Attenuation constant, Nepers per meter. Okay. Okay, what is the relation between Nepers and decibels? Okay, see here. 1 Nepper equal to 8.686 dB or 1 dB equal to 0.115 Nepiers. Okay, and phasor currents and voltages. Okay, what is the necessity of going towards exponential forms instead of trigonometric form? What is the purpose? Okay, here attenuation constant or phase constant or the traveling wave of a transmission line is always represented in terms of exponential increasing or decaying function. That's why it is best suitable to analyze that sine wave or cos wave in terms of exponential form is okay, quite advantage, okay, for that analysis. That's why uh, the cos function is represented here as a cosine, exponential function. Okay, from that we define uh, sorry, alpha, beta, and gamma terms. Okay, what is the relation between alpha, beta, and gamma? Gamma equal to alpha plus j beta. Okay, and just like current components in transistor, here alpha, beta, gamma also having some relation. Alpha equal to, sorry, gamma equal to alpha plus beta. Here, beta is the imaginary term, alpha is the real term. Okay, where alpha equal to attenuation constant, beta equal to phase constant. That phase constant is also called as a wave number. Wave number. Okay, where gamma is called propagation constant. Okay, remember that. Phasor currents and voltages. Okay. In the traveling wave voltage Vx is represented as V naught into e power minus gamma z. Current in terms of I naught into e power minus gamma z. Okay, the same expression. See here when the transmission line model, when we consider the low frequency. Okay, at low frequency, these are the significant. Okay, at low frequency, only resistance has to be considered. At higher frequencies, capacitance and inductance must be considered. Why? Why they prefer like this? Low frequencies. Already I told you the difference between resistance and impedance, right? Similarly, what are the parameters which affects the frequency components? Okay, inductance, j omega L, capacitance, j omega C. Okay, these two are imaginary terms. Moreover, they are frequency dependent. Okay, see here. Okay, single section of a transmission line. And when we consider one segment of a transmission line, what is the expression here? Okay, we will see in the last class. Okay, Vz equal to minus of r plus j omega L into Iz by gamma. Okay, similarly, Iz equal to minus g plus j omega C Vz by gamma. Okay, similarly, from that we defined characteristic impedance. What is meant by characteristic impedance? Characteristic impedance, simply the ratio. Impedance is nothing but resistance. Resistance is defined as voltage by current, right? Here, that resistance or impedance is simply defined as Z equal to V by I. Okay, R equal to V by I. Okay, just like a Ohm's law. Here, Z not equal to Vz by Iz, voltage by current. You already know what is the expression for Vz and Iz. Okay, in the earlier slide. See here, Vz equal to R plus j omega L into Iz by gamma, Iz equal to G plus j omega C into Vz by gamma. From that, Vz by Iz equal to R plus j omega L into Iz by G plus j omega C into Vz. That's all. Vz by Z is nothing but Z naught. So Z naught equal to square root of R plus j omega L by G plus j omega C. This is the fundamental expression for the characteristic impedance. Remember that point. It's very, very important. Z naught equal to square root of R plus j omega L by G plus j omega C. Okay, all the derivations depends upon this relation only. Okay, for the Z naught. Similarly, gamma is also defined. Okay, in the later sections. See here. Okay, how it is important. Okay, to define different transmission lines. See here. For suppose when I'm told you the transmission line is said to be lossless, and if the transmission line is lossless, and if the signal is propagating through the transmission line, okay, whatever it contains, the amplitude at the sending level is same as signal amplitude at destination point, and both are same. Why? Because there is no loss. Okay, means when there is no loss means there is no resistance. Okay, there is no dielectric conductance. Okay, it means R equal to 0, Z equal to 0. But when the transmission line is said to be lossless, then R equal to 0, G equal to 0. These two terms are 0. When these two terms are 0, Z naught becomes Z naught equal to square root of J omega L by G omega C. J omega C. J omega. Both are cancelled. Square root of L by C. That is the characteristic impedance of a lossless transmission line. Remember that point. It is very, very, very important in the competitive exams also. Okay, Z naught equal to square root of R plus j omega L by G plus j omega C, where Z naught is the characteristic impedance or is the conductor resistance in ohm per unit length. L is the inductance. And ohm per unit length means ohm per unit length means per segment. Okay, for each segment, the resistance value it is. L is the inductance in Henry per unit length. G is the dielectric conductance. Okay, in what are the units of conductance? Resistance. What are the units of resistance? Ohms. Okay. Similarly, what is meant by conductance? Inverse of resistance is treated as a conductance, right? For that, resistance units are ohms. So conductance units are reversed to resistance and a mhos. That is simply uh, inverse. Okay, and a reverse that symbol. Okay, this is called mho. Okay, this is called mho. This is called ohm. Okay, that is the symbol of ohm. OHM, right? Okay, sorry. Ohm, OHM, ohm. When we reverse that ohm symbol, that is called MHO, mho. Okay, that is the symbol of mho. That symbol of mho is also called as the Siemens, SIMENS. That is the symbol of S here. Okay, remember that point. Okay, Z naught is the characteristic impedance, R is the conductor resistance, G is the dielectric conductance in Siemens per unit length. Okay, C is the capacitance in farad, in farads. Okay, capacitance measurement is in farads. Okay, dielectric conductance Siemens, inductance Henrys, resistance ohms. Okay, remember that. Okay, for an RF line, R and G are zero. Okay, here RF line means here no, lossless. Okay, and they tend to uh, intimate that information as the RF line instead of lossless. Okay, for an RF line, R and G are zero. Okay, that is also called as a lossless condition. R and G are zero means that is a lossless condition. Okay, that is entire is valid through entire radio range of frequencies. Okay, what is meant by radio frequency range? The frequency which is liable to radiate, and from which frequency range that signal is able to radiate, that is called RF frequency. Okay, so Z not equal to square root of L by C. Why? Because R equal to 0, Z equal to 0, G equal to 0. Okay, get it? Okay, that is the concept of characteristic impedance. See here. Okay, and next one is the velocity factor. They mentioned with velocity factor. Velocity factor means how fast it is moving through transmission line. Okay, that is the velocity factor. See here, step moves down line at a finite speed. The velocity cannot be greater than the speed of light and usually lower. Okay. And if what is the ideal flow of ideal speed of that signal? In general, the light velocity is the free space. But when we consider a one uh, independent medium, okay, and that is independent medium of medium, not like a free space. Okay, and the medium, okay, whose medium characteristics are quite different from free space. Okay, what are the medium characteristics of the free space? Can anybody tell me? What is the permeability of the free space? What is the permittivity of the free space? What is the intrinsic impedance of the free space? Do you know? Free space. Okay, the permittivity of the free space. Okay, 4 5 into 10 power minus 7. Permeability. Okay, 8.854 into 10 power minus 12. Okay, intrinsic impedance of the free space, 377 ohms. Okay, they are the standard for free space. Okay, and relative permittivity is also one, is always one. Okay, just I am told you epsilon naught and mu naught. Okay, that is the concept we have to study it in electromagnetic waves part. Okay, the second part of our syllabus. Okay, see here, here velocity cannot be greater than a speed of light and usually lower. Okay, and when we consider a other than free space medium. Okay, that is the situation here. The velocity factor is the ratio. Oh, okay. Velocity factor. What is the necessity of velocity factor defining here? Okay, when I am propagating the signal in free space. Okay, that is the one part. When I am propagating the same signal in one transmission line. Okay, which one receives the load first? Okay, for suppose I am teaching the same class. Okay, and I am teaching the same class. Uh, uh, with one wireless medium and wired medium, wireless medium and one wired medium. Okay, which mean which one receives? I mean, from which medium you are able to receive the signal first? Okay, obviously that wireless medium. Why? Because in the wireless medium, free space is the medium between you and me, where the signal propagates at a rate of 3 into 10 power 8 at a light velocity. Okay, when we consider the medium, when we consider the wired medium, okay, it definitely it takes okay, a few milliseconds to microseconds delay, obviously. Okay, then how do we define that velocity factor and how much factor the signal is delayed when we consider the wired medium? Did you get the point? Did you get the point? Here I am considering the two cases. Okay, case one, when we considered wireless medium and a free space as a medium between you and me. Okay, second part, here I am considering a wired medium and in between you and me, some cable is connected. Okay, okay, at the source end I am teaching the class, at the destination end you are simply listening the class. Okay, and when we consider the case one, when we consider the case one, okay, in between you and me, the medium is wireless medium and a free space. Okay, in free space the signal is propagating with a velocity of light, right? And 3 into 10 power 8 meters per second. Okay, when we consider, okay, just consider that is the ideal case. When we consider the wired medium and you and me is connected with a one wired medium. Okay, and I mean, is it the signal is propagating with the same velocity of that light when we consider the wired medium? No, not at all. Okay, but definitely the speed of that signal propagation decreases compared to that case one. But how much factor it decreases is the velocity factor. You get it? Okay, that is the velocity factor. Okay, now okay, the author defined here, I don't know, but actually that is the velocity factor, and that is the way of definition. See here, okay, how they define that velocity factor here. See here, velocity factor is the ratio between actual propagation velocity and speed of light. Okay, here also they define like this. Okay, velocity factor here define here. See, observe that velocity factor is the two terms, velocity and factor. Okay, see here, and from the known parameters. Okay, I want to classify these two. What is meant by ripple factor in electronic EDC subject? Ripple factor. What is meant by ripple and what is meant by factor? And what is meant by ripple factor? Okay. Again, there are two terms. Ripple factor, right? Ripple means how much AC content present in rectified output is the ripple. Okay. Sorry. Okay. The presence of AC content in rectified output is the ripple. Okay. But factor means how much quantity that existed. And when we consider the half rectifier, how much AC content existed in the rectified output? Okay, 1.21 or simply 121% of AC present in the rectified output and more than input. Okay, there exists more than input. Okay, when we consider the full rectifier, okay, 48% of AC. And ripple content means AC content present in rectified output, but how much quantity is the factor? Similarly, here also velocity factor means, okay, factor is always the number. Okay, factor is always the number. And how much factor it decreases when compared to the velocity of light. Why I'm saying decreases? Okay, the ideal condition is the velocity of light. Okay, that is the highest speed. With reference to that highest speed, when we consider the transmission medium, that speed is always less than that light speed. Okay, that's why that is always decreases in comparison with the actual reference value. Okay, the velocity factor is a ratio between the actual propagation velocity of the wired medium with respect to wireless medium. Okay, that wired medium is simply they mentioned as the actual propagation velocity, and the speed of light means that wireless medium. Did you get it? That is the velocity factor. Okay, velocity factor depends not only on line dielectric characteristics. Okay, what is meant by dielectric characteristics of that medium? Okay, whatever I told you, no. Okay, permeability, permittivity, free space impedance. Okay, all those parameters are called medium characteristics or medium dielectric characteristics. Okay, and the medium, how fast the medium propagates the signal depends upon that medium characteristics. That medium characteristics. Okay, that's why that velocity factor is also depends upon, okay, that dielectric line characteristics. See here, velocity factor. Okay, light velocity. Okay, of course you don't know c equal to 1 by square root of mu naught epsilon naught. Okay, and at this time, why? Because actually this topic is from electromagnetic wave theory, but the electromagnetic wave theory is not yet covered. But according to the syllabus, and just remember this point only. Okay, no need to derive all those. Okay, while dealt with the electromagnetic theory, I mean electromagnetic wave theory, at that time, okay, you able to know what is the relation between that mu naught, e naught, epsilon naught, and c, light velocity. See here, c equal to 1 by square root of mu naught epsilon naught, and mu naught epsilon naught are the medium constants. Here mu naught is nothing but 4 pi into 10 power minus 7, and epsilon naught equal to 8.854 into 10 power minus 12 epsilon naught. Okay, and when we simplify this expression, we get 3 into 10 power 8 or 300 into 10 power 6 meters per second. Okay, that is the velocity of light. Okay, see here, velocity factor means how much factor it decreases. See here, velocity factor notation is VF. Velocity factor notation is VF equal to V suffix P and velocity. Okay, velocity, propagation velocity of a signal in lined, I mean something, what they call medium. Okay, wired medium, propagation velocity in a wired medium. Okay, wired medium, how much factor it decreases? By c. Okay, see the speed of light in a vacuum, in the ideal case. Okay, and when they ask what is the velocity factor, okay, simply you have to mention velocity factor. Okay, velocity of a wave in wired medium with respect to wireless medium. Okay, then you are able to get that velocity factor. Okay, remember that point. Okay, and what we learned so far, what is meant by velocity factor. Okay, what is meant by characteristic impedance? Characteristic impedance of a RF line, okay, radio frequency line, or simply lossless line. And the next factor, next parameter is the propagation constant. Okay, already I told you propagation constant represented with gamma, right? Propagation constant is represented with gamma. Okay, characteristic impedance is represented with Z naught. Okay, and what is the relation between alpha, beta, and gamma? Okay, what is the relation between alpha, beta, and gamma? Okay, gamma equal to alpha plus j beta, where alpha is the attenuation constant. Okay, okay, why I'm repeatedly uh, I mean repeat this concept. Yeah, why I'm frequently repeated this concept means, okay, these two are very important in the competitive examination point of view and your final examination point of view. Okay, why? Because this is the only concept. Okay, this is only the concept you must okay, learn, and you must aware from the transmission lines. See here, propagation constant. Already you know the expressions is equal to minus r plus j omega l into I z by gamma. That's why I am told you remember this expression. Okay, every time you best utilize this expression. Okay, gamma into vz, gamma into iz. Okay, minus of r plus j omega l into iz, minus of g plus j omega c into vz. Okay, these are the fundamental expression for propagation constant, characteristic impedance. In order to define the medium is okay, wired or wireless. Okay, I mean for the wired mediums, is it lossy or lossless? Okay, see here, gamma equal to alpha plus j beta, and phase velocity equal to omega by beta. Already you know. Okay, see here, in previous case, to define that characteristic impedance Z naught, simply we define. Let us consider this is the equation one, and this is the equation two, right? Equation one and equation two. In previous case, we simply would define equation. I mean, to define characteristic impedance, simply we define equation one by equation two, and divide equation one with equation two, right? But for the definition of propagation constant, simply I am multiplying 1 into 2. For the characteristic impedance, 1 by 2. Okay. For propagation constant, 1 into 2. Okay, see here, gamma into gamma, gamma square, vz into iz, vz into iz equal to minus into minus plus r plus j omega l into g plus j omega c, r plus j omega l into g plus j omega c, iz into vz. That's all. So from that, gamma equal to square root of r plus j omega l. Okay, vz diz cancel, vz diz cancel. Okay, vz diz cancel, vz diz cancel. Gamma equal to square root of r plus j omega l into g plus j omega c. Okay, again consider the previous case, and when the transmission line is said to be lossless. Okay, and when the transmission line is said to be lossless, then there is no lossy components. Okay, r component and g component. When r equal to 0, g equal to 0, what we get? Gamma equal to square root of j omega l into j omega c. J into j square. J square is nothing but minus 1, right? Omega into omega, omega square, L into C, LC, right? J square, omega square, LC, J square, omega square, and root both are cancelled. So J into omega square root of LC. Okay. Okay. Here the propagation constant is purely imaginary. Okay. Here the propagation constant is purely imaginary for lossless condition. Means there is no attenuation. Already you know gamma equal to alpha plus j beta, right? Gamma equal to alpha plus j beta. Compare real and imaginary terms on both sides. Okay, gamma is replaced with alpha plus j beta, alpha plus j beta equal to j omega into root LC, and alpha equal to 0, right? So gamma equal to alpha equal to 0, beta equal to omega root LC equivalent. Okay, but what actually phase velocity means? Phase velocity equal to omega by beta, right? Omega by beta. Okay, from that we get 1 by root LC. Okay, in the previous case and this case, okay, both are same or not? And we are defining lossless condition for that characteristic impedance or okay, phase constant. Okay, so phase velocity equal to square root of root L by C. Okay, did you get it? Okay, is it clear? Clear, everybody? Propagation constant, characteristic impedance, and velocity factor. These two are very, these three are very crucial. So next concept is okay. The next concept is metallic transmission lines. Metallic transmission lines. Okay, see here. Here already you know different types of transmission lines. Okay, different types of transmission lines in the earlier class. See here, when we consider the two-wire parallel transmission line, when you consider two-wire parallel transmission line, okay, here when we consider the two-wire parallel transmission line, how many uh, transmission lines, I mean how many wires it contains? Okay, the name itself indicates it contains two wires, right? See here, these are the two wires. Okay, this is the wire 1 and this is the wire 2. These two wires are spaced apart some distance. Okay, these two wires are spaced apart some distance d. Okay, that two-wire parallel transmission line characteristic impedance Z0 is 276 into log of d by r, where d is the separation between two wires. Okay, and what is meant by r here, where r is the okay radius of that piece of transmission line, single wire. Okay, and its phase velocity is 1 by square root of mu naught into epsilon. Mu naught into epsilon, where epsilon is nothing but epsilon naught into epsilon r. Of course, this is not the part of covers, but just remember those values. Okay, Z naught is the characteristic impedance, D is the distance between the centers, R is the radius of the conductor, epsilon naught is the permittivity, epsilon r is the relative permittivity, mu naught is the permeability of a free space. Okay, similarly for the coaxial cable, okay, okay, these are all not required. Okay, from this concept, it is ours again, reflection of a voltage step. Okay, but before going to that, okay, I want to explain okay, this topic slightly. But okay, it's already 9:52. Okay, so just leave it. What we learn from this today's class: characteristic impedance, velocity factor, and propagation constant. Okay, of course, it's derivation parameters for both line and I mean lossy and lossless. Okay, and basic expression. The basic form of the expression is the lossless or lossy. But when we apply okay, R equal to 0, G equal to 0 condition, that is called lossless condition. Okay, that's all about today's class. I will continue in the next class. Okay, in the next class we will discuss about uh, reflection coefficient and VSWR terms. Okay, thank you.